Number 7. A person lifts a 4.5 kilogram cement block a vertical distance of 1.2 meters and then carries the block horizontally a distance of 7.3 meters. Determine the work done by the person and by the force of gravity in this process. Now, first thing to talk about is this whole 1.2 and 7.3 deal. When you lift something up, are you most certainly applying a force upward and it's moving upward? Yes. No doubt about it. But if you carry something sideways, oddly enough, you're not truthfully applying a force to the thing. The sideways motion when you're carrying something does not count. Okay? You're not applying an upward force. If you want to think about it as angles, you lift it up, it went sideways. That's a 90-degree angle. The force was upward, the motion was sideways. That doesn't count. So you can look at it one of two ways. Either you got the 90-degree thing going on, or simply carrying things is not applying forces to them. If they had said he pushed the box 7.3 meters, you totally have work happening. But that's not what happened. He carried it. Therefore, the 7.3 doesn't count. So on to the whole how much work was done. When they say you lifted a vertical distance here, you are clearly having to fight the force of gravity. So when you want to do work, and you want to say force times distance, well, the distance is 1.2. Force is going to have to be 4.5 kilograms times g. And when you do that calculation, you're going to get a number in the 50s, and that'll be your answer for how much work did the worker do. At the same time, how much work did gravity do? Well, as you're given no other information, you have to assume that gravity just did the same amount of work, just in the opposite direction. It was resisting you. On to number 8, airplane. This plane has a vertical takeoff. It's got a mass of 8,000 kilograms, and it's got an acceleration of 1, and it goes up 30 meters. Well, work is force times distance, so mass times acceleration times distance. 8,000 times 1 times 30. That's that problem. On to number 10. Number 10 gets people frustrated. So here on number 10, we've got the flight attendant pulling her bag. And you say, I gotta set myself a little suitcase here. They say it's a 70 Newton suitcase. That is the weight of the suitcase. Gravity is doing that work. Then she pulls it with 40 newtons. She pulls at a constant velocity. That's important here because that means forward and backward are in balance. And she goes 253 meters at 52 degrees. Is that right? Right? 52 degrees. I didn't write that down. So, first question. What's the work done by the flight attendant? Well, the force done by the flight attendant is 40 newtons. The distance traveled by the flight attendant is 253 meters. And of course, I forgot. I gotta write this in here. Work goes force times distance, cosine of theta. Cosine of Greek. Cosine of theta. Okay. So, and that's where that comes into it. So, she applied 40 newtons of force for 253 meters times the cosine of 52 degrees. Done. Part B. What is the work done by friction? Well, we said that she's going at a constant velocity. That means the horizontal component of her force is equal to the force of friction. So it's going to be the exact same answer as you just got, just negative. And part C is 100% just a friction question, and I do not expect you to calculate that. So you can just cross off number 10, part C. And let's look at number 11. A person drops a ball from the top of a building, and another person on the ground observes the ball's motion. Each observer chooses his or her own location for the level as 0. And for potential energy, will the calculations of the values for, so we're making comparisons, and it is very much a perspective question. So let's grab a building. Okay, you've got one person at point A, and you've got another person at point B. And the question is saying, if I drop a ball if we drop a ball, will they agree on this and that? So as the ball falls, the potential energy associated with the ball, will they agree on potential energy? If they both consider their location to be 0, will they agree on potential energy? Well, if letter A considers their position to be 0, they're going to think it has no potential energy. However, letter B is going to see the ball as having some height, and therefore some potential energy, so they will not agree. The change in potential energy. Now here's where they'll have an agreement. A will see the ball fall below 0, and let's just say it was 100 joules. A will see the ball lose 100 joules. B will see the ball go from, say, that 100 joules down to 0. So they will both witness the same negative potential energy happen. It'll be the same loss of potential energy. So they will agree with that. The ball's kinetic energy. Nothing to do with perspective here. The ball's going to have a certain speed. It's going to have a certain kinetic energy. So they will agree with kinetic energy. So in rewind, they will disagree about the potential energy at their place. They will agree in the change in potential energy, and they will agree with the ball's kinetic energy.